Solving exponential equations. So we have a property of equality for these exponential equations that will be key to solving these. So here's the algebra speak. If b is a positive real number other than 1, and b to the x is equal to b to the y, if and only if x and y are also equal. So here's what this means in actual everyday English. So basically, if we have 3 to the x equals 3 to the 5th, because their bases are the same, then that means that x is equal to 5. When the bases are the same, you can set the exponents equal to each other. And you also have, well, if I go the other way, if I know that x is equal to 5, then I can raise these both to the same base, like 3 to the x and 3 to the 5th. I could also do 4 to the x and 4 to the 5th, 6 to the x, 6 to the 5th. As long as the bases are the same, the exponents are equal. So here's the general steps for solving equations with the same base, or something that you can make into the same base. Rewrite the problem using the same base for both sides of the equal sign. So like if we look at example 1, 2 raised to the x plus 6 equals 2 to the 5th. So in this case, the bases are both the same. So I don't even have to worry about step 1 because the bases are already the same. They're both 2's. Then, use the property of exponents to simplify if necessary. Well, I can't do anything with pluses in the exponent, and I can't do anything with just a plain old 5. Step 3, drop the bases and set the exponents equal to each other. So that's the first thing I can do. So since the bases are the same, I don't need them. That means I can take this exponent, x plus 6, and set it equal to the other exponent of a 5. This I can solve very quickly. Subtract 6 from both sides of the equal sign. So x equals to negative 1. And there's my solution. Done. Let's look at example 2. That's not quite so straightforward. So example 2, I have 100 to the x equals 1/10 to the x minus 3. So step 1 is I need to get the bases the same. Well, I know that 100 I can make into a base of 10 because I know that 10 squared is equal to a 100. So I'm going to rewrite this 100 as 10 squared. But I also still have to remember that I have that 100 to the x power. Because if I simplified this down, 10 squared gives me 100, and 100 to the x is just 100 to the x. Now let's look at the right-hand side. 1/10, well, I can use my exponent rules with negatives. 1/10 is the same as 10 to the negative 1 power. So this will be equal to, I'm going to have 10 to the negative 1 power, because 10 to the negative 1 is the same as this 1/10 piece, but I still have all of that raised to the x minus 3. That's step 1. Now that they're both in base of 10, base 10, base 10, I'm getting close. So now, before I drop the bases, let's instead use properties of exponents to clean this up a little bit. So the property I'm going to use with this is the a to the m all to the n, means you're going to multiply the exponents together. So on the left side, I'm going to have 10. 2 times x makes 2x equals 10 to the, now on the right-hand side, it's not quite as simple. It's going to be negative 1 times the entire x minus 3. So we're doing a lot of math inside the exponents. So distribute this negative 1. So I have 10 to the 2x equals 10 to the negative x plus 3. Now that my exponents are simplified and the bases are the same, now I'm going to drop the bases, because they're both 10s, I don't need them, and set their exponents equal to each other. And this is simple enough to solve. I'm going to add x to both sides. 3x equals 3. Divide by 3, and we have x is equal to 1. Your hardest piece will be trying to get these bases to be the same. That's your hardest piece of work, is getting these bases to be the same, because it's like a giant puzzle. That's all these are. Example 3. Solve 9 to the 2x minus 5 equals 27. Okay, well, 9 and 27, I know those are both powers of 3. So for example, 9, I know that I can make 9 into 3 squared. So what I'm having now is 3 squared to the 2x minus 5 power. because the 3 squared takes place of the 9, but I still have the 2x minus 5 and the exponent. Now I also know that 27 is 3 to the third. But since 27 is just a single number, I don't need parentheses or anything. I can just replace it as being 3 to the third. So now I have the bases are the same. They're both 3's. Now I'm going to use that property of exponents again. A to the m to the nth power means multiply your exponents to kind of clean up my exponents a little bit. So this is going to be 2 times 2x minus 5 equals 3 to the third. And now distribute in your outside 2. 3 to the 4x minus 10 equals 3 to the third. Now that your exponents are cleaned up and the bases are the same, we can drop our bases and set our exponents equal to each other. Solve for x. Add 10 to both sides. 4x equals 13. Divide by 4. And x is equal to 13 over 4. Fractions are okay. It's not the end of the world. Example 4. Solve 4 to the 2x plus 3 equals 1 over 32 to the 3x plus 1. So the two numbers I'm working with, 4 and, well, 32, I know those are both powers of 2. 4 is the easy one. I know that 4 is equal to 2 squared. That's the easy one. 32, I know is 2 to the 5th. But I don't just have 32, I have 1 over 32. Well, that means I need to make this 5 a negative. Since it's a fraction, that's what negative exponents do. They knock that base down to the bottom of a fraction. So let's go ahead and start replacing. 4 gets replaced with 2 squared, but then I still have this 2x plus 3 exponent on the 4 equals 1 over 32 gets replaced with 2 to the negative 5. There we go. But I still have this exponent of 3x plus 1 on that 1 over 32. Now let's use our property of exponents and multiply the exponents together since they're raised to each other. So 2 and then 2 times 2x plus 3, all in the exponent, equals 2 to the negative 5 times 3x plus 1, all in the exponent. So let's clean this up. So 2 times 2x, we have 2 to the 4x plus 6 equals 2 to the, distribute out the negative 5, negative 15x minus 5. Okay, now bases are the same, exponents are cleaned up. That means I can drop these bases and set the exponents equal to each other. Solve this for x. So add 15x to both sides, get your variables on one side of the equation. Get 19x plus 6 equals negative 5. Subtract that constant, so minus 6 from both sides. 19x equals negative 11. Divide by 19. X is equal to negative 11 over 19. So that was solving exponential equations with the same bases. Well, what happens if I can't make the base the same? So for example, if we look at 5, we have a base of 5 and a base of 18. There's no number that I can raise 5 to get me anything with raising 18. It's not going to happen. So we have another way to deal with this. And this also does work even if you can make the bases the same. So if you get stuck, this always works. So when you don't have the same bases, you're going to take the common logarithm or the natural log of both sides. Now, the only time you use the natural log is if you have e as one of the bases. It's the only time you're going to use that natural log. Anything else, we're just going to use a common logarithm which has a base of 10. So let's look at example 5, one step at a time. So 5 to the 2x minus 3 equals 18. Since I cannot make these be the same base, I'm going to take the log of both sides. So log of 5 to the 2x minus 3 equals log of 18. That's step 1. Step 2 is I'm going to use the property of logarithms, that power rule that we had. So that said, if it was log of x to the m, I could take that exponent and put it down in the front and make it m times the log of x. So I'm going to use that here. I'm going to pull this down to the front, and I'm going to keep it in parentheses since it's more than one thing. Now I have log of 5 equals log of 18. Okay, now remember, it's x we want. So log base 10 of 5, this is just a plain old number. I know it looks funny, but it is just a number. So this is multiplying, so I want to get rid of it. So I'm going to divide out the log. That's the next step. So now all we have is 2x minus 3 equals log of 18 over log of 5. Now, this right-hand side, there's no variables on that right-hand side. So this gigantic fraction thing right here, this is just a number. So use a calculating tool to approximate this decimal. Approximate with calculator of some kind. I'll put a link on your Google Classroom. So approximate this decimal, log of 18 over log of 5, and you're going to get 1.796. Make sure you round properly. Give me about 3 decimal places. Now I can finish solving this for x like a regular equation. Add 3 to both sides, so I get 2x equals 4.796, and divide by 2, I get x is equal to 2.398. And that's it. Let's try another one. Example 6. 8 to the 4x plus 1 equals 205. Okay, cannot get 8 and 205 into the same base, pretty sure anyway. So instead of sitting here for 5 hours trying to figure out what power of 8 will get me something that's similar to the power of 205, I'm just going to take the logarithm of both sides. So I'm going to take log of 8 4x plus 1 equals the log of 205. Okay, now I'm going to use my exponent property of logarithms to pull my variable, which is in the exponent, down. So in parentheses, 4x plus 1 times the log of 8 equals the log of 205. Now again, this is being multiplied, so to get rid of that log, I need to divide it out. So my log on the left, make a 1 and cancels out. And we have log of 205 over log of 8. Now again, this crazy business right here is really just a decimal number. So use a calculator to approximate that decimal, and you get somewhere about 2.56. And then continue solving this for x like a normal equation. Subtract the 1, 4x equals 1.56, divide by 4, x is equal to 0.39. Example 3. Solve e to the 4x minus 9 equals 56. Again, I can't make e into anything because e is that irrational number that never ends. So since it doesn't end, I'm not going to be able to get a whole number out of it, no matter what power I raise it to. So I need to take the log of both sides. But since I have a base of e, I don't want to take the common logarithm like I have been. I want to take the natural log, ln. E to the 4x minus 9 equals the natural log of 56. What you do to one side, you have to do to the other. Use your exponent property of logarithms to pull this 4x minus 9 down to the front. So again, in parentheses, 4x minus 9 times the natural log of e equals the natural log of 56. Now, here's where we're coming to something kind of cool. Natural log of e, well, if we remember, the natural log has a hidden base of e. So when your base and your argument are the same, that's the inverse. This is a 1. That can be said the same for log base 10 of 10. That's a 1. Log base 2 of 2. That's a 1. Log base 8 of 8. That's a 1. Anything that follows this pattern is equal to a 1. So instead of having to divide this out, just leave it alone. This is really 4x minus 9 times 1. That's really what that turns into. Equals natural log of 56. Well, 4x times minus 9 times a 1, well, that's just 4x minus 9. So natural log of e kind of went away all on its own. So I'm going to show you two different forms of this answer. Instead of finding a decimal approximation for this, I'm just going to leave it alone. Here's what we're going to do. We're going to keep solving. Plus 9 to both sides. So 4x equals, so natural log of 56 is a number, but I just don't know what it is. So we're just going to leave natural log of 56 alone. Then we're going to do plus 9. Then we're going to divide by 4 to everything. And we have x equals the natural log of 56 plus 9, all divided by 4. So what we have here is this is what we call an exact solution. This is not a decimal approximation. This is the exact solution. This is like leaving 1/3 as 1/3 instead of approximating it as 0.33. Now, you could, it doesn't matter, it just depends on how your answer choices are written, you could get the decimal approximation by substituting natural log of 56 into a calculator, and you're going to get something around the lines of 3.256. This is the approximate answer. These are the same thing. So if you have natural logs in your answer choices, or logs in general, you have an exact solution. If you have decimals, you have an approximated solution. Either of these are both correct answers.